Welcome to video number 7 in the Foundations of Computational Economics course. In this video we will continue looking at the Python essentials, and we'll talk about the object-oriented programming. There are several styles of writing computer code. Procedural programming is about writing a series of computational steps where blocks of the steps can be singled out into functions. So this is the most typical or easy and simple way to write computer code. Functional programming is a completely different style in which instead of working with data and computational steps, the coder is writing a series of functions such that the combination of these functions produces the required results. Finally, the object-oriented programming is the style which is based on writing a distinct pieces of software which combines both data, called attributes, and functions, which are properties, or methods of these pieces. So let's quickly review these three styles. So imagine we need to produce a sequence of Fibonacci numbers. Under procedural programming, we could write a function over here, Fibonacci procedural, and then call this function in the main body of the program. So let's see what happens here. The function takes 3 inputs, n, and it produces the sequence of numbers up to n, so that's the upper bound. And then it takes the first and the second members of the sequence, and of course for the standard Fibonacci these are 1 and 1, but it could be a Fibonacci-like sequence started from a different numbers. And let's see what happens here. Well, first we're creating the list of zeros. This multiplication here stands for repeating the element of the list so many times, or n times. And then in the first 2 elements of the list, indexed 0 and 1, we put the first and the second number in the sequence, and then just going from the third element, remember range starts at the... Oh, I'm sorry. The range can have 2 arguments, where the first argument would be the index of the starting member, and it goes all the way up to n. We can update the elements of the list according to the standard Fibonacci formula. Now observe that I minus 1 and I minus 2 are both well defined here because we're starting from the second step. All right, now we can in principle initialize this sequence with any numbers, but let's do it with 1 and 1, and then just call this function Fibonacci. It returns a list, so we can then take a for loop with the elements of this list and print them, and that's what we get. Right, sort of very usual way to write the code. In functional programming, things are a lot more interesting and different. So look at this function. This is a variable, right, which holds a function defined as lambda function of 3 elements, 2 of which have default values. And then what does it do? Well, it basically just returns something that it computes in these 2 lines here. And what does it compute? It says it's going to be an empty list if n equals 0. Otherwise, and remember this is our 1-line if statement, the ternary condition. Otherwise, it will return the list passed as a first argument, plus whatever this function itself returns when called with a different set of arguments. And what are the different arguments? The n minus 1, so it's like we're asking for the Fibonacci sequence of 1 less length, and we're passing second in place of the first element, and the sum of the first and the second in place of the second. This is a little bit hard to grasp immediately, but essentially we're doing Fibonacci calculation here, where we're replacing the element of the list with the next element, and the next element we're replacing with the sum. So interestingly, when we run this code and run this loop, which basically prints out the numbers, we get exactly the same answer. Wow, interesting. Magic. So here's the explanation of what this function does. And this code introduces an interesting concept, which is worth noting, which is a recursive call of a function. The function in any programming language can call itself absolutely fine, and that creates this sort of a chain of functional calls. It's important that the chain terminates somewhere, and here, because we're calling each time with n less than the previous call, and the function terminates when n equals 0, that's how this chain stops eventually. But let's include an additional statement here, which would print a dot every time a function is called, just to see how many times it's called in this chain of recursive calls. The way to do it with lambda functions is to include an OR statement and something to be done, and here we're just printing a dot, and it will return true or false depending on the success of the operation, or whatever it returns can be interpreted in the Boolean way. But whatever this returns, we still need to compute the rest of it because of the OR operand, right? So to calculate the result of the whole call, we have to evaluate both sides of the OR operator. And here we'll get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of these dots. So the function was called 11 times, and that's quite natural. We start with 0, and then we go all the way to 0, right, to n equals 0, when it does nothing, but it still prints the dots. And the result is the same. So here's functional programming for you. There are a completely separate sort of group of languages like Haskell, which are functional languages, and this is a different territory from what we are doing in this course, but it's nice to know about this classification. Now, how is the object-oriented programming? How could this Fibonacci function or code look there? Well, in the object-oriented programming, we're writing classes instead of functions, or together with functions. And so this block of code that I've highlighted, it defines a class Fibonacci, which has some data stored right inside of that class. And this data is going to give us the standard two starting elements of the sequence. And then there are what looks like functions, and they are functions defined inside of the class, and then they're called methods. There are two methods defined here. This is one, and this is the other one. The first method, and each class should have one, is called initializer or constructor of a class. And it basically is run when the class is used to create an object. Here we're just storing the size of the sequence that we want to return, that we want to calculate, inside of what's called self-n, which is a public attribute of this class. And then another method, another function inside of the class defines the method which is called when we are writing the class, the object name with parentheses. So we're using the objects produced from this class as functions. And if we do, then this method is called here, and it basically does the work similar to how it was done in the procedural programming style. So you can think of object-oriented programming style as functions combined within classes, but the characteristic attribute here is that the data is also stored inside of objects with the functions. So let's run this one. And you can see we also run it in a slightly different way. So first we create an object using the class Fibonacci and initializing this object with 10 as a size of the sequence that we want to return. And I'm just printing here the type of f. F is becoming a variable, and you can see that it becomes a variable of the type Fibonacci. So by writing classes, we are actually defining new variable types. Remember, last video ago we talked about the user-defined functions. Now we're talking about user-defined types, data types. But then we can just call this object by writing f and the brackets, and it will return the sequence of the Fibonacci numbers that we can then put into a for loop and print these numbers, and we get the same result. All right, so now with that we've started talking about the object-oriented programming. You've noticed that we are now using new terms: classes, objects, attributes, properties, methods. Well, this is not complicated at all. So you can think of a class as being a blueprint, a design, a safe design for creating objects. Objects are also called instances of the class. A class would define some variables, data inside of that class, and that data can be of any types. The data becomes attributes of the objects. So the attributes of the objects are created from the attributes listed in the class. And then the methods of the objects, they are created according to the blueprint in the class, which defines the methods of the class. And that's all there is to it. It's really that we're writing code such that we're defining this, units of the code where we can store data and methods to work with this data together. Now, why is this useful? Well, there are what's known as principles of object-oriented programming. So the first principle is called encapsulation. And it usually goes together with abstraction. Well, you've noticed we are combining functions and related data in one place of the code. And moreover, we have an ability to expose only the needed data, only the needed attributes, and only the needed methods. Needed for what? Needed for any other code that uses this sort of an object. And by this, we can hide away some of the functionality of the inner machinery of this class and the resulting objects. And then what that allows for is that, we can later come back to this code and maybe fix an error or optimize it, do some changes to the inner part of the class, and we can be absolutely sure that no other code will be broken, right? Because if the class does not expose certain methods or properties or attributes, then no other code could ever use them. And therefore, it would be safe to change if needed. Now, inheritance is something that allows classes to build sort of trees. So classes can be built from other classes, and when this is done, then the children classes, they inherit the properties and methods of their parents. And that essentially allows to save on lots of code writing. So if you have a class of some general polygon class, and then you want to create a rectangular class, you can say, well, it's a polygon, so everything that applies to a polygon applies here, but it has only 4 vertices, and all of the sides have to be parallel. Oh, and the angle has to be right. So you can define classes which are special cases from classes which are general, and inherit all of the properties which already applied to the more general class. Finally, polymorphism allows us to write methods which look the same, but they are applied to different classes. So, for example, we can have an operation with the same name, which is defined slightly differently for different classes, and we'll look at that in a second. So I've written a piece of the code here which allows us to look at the inner structure of a class. And this function is going to be called Object Explorer. It's not too long, and you know, you can study what it does on your own. Let's not let's think of this as a black box for now. I guess what I should have said is on the previous slide is that I'm using this special command in Jupyter, a double percentage sign. This is called a magic command, or a magic for short. And the content of this cell will be written in a file which I named ObjectExplore.py. So this brings us a little bit back to the discussion in the one of the early videos where I was saying that Jupyter notebooks are really useful when we are presenting the code and presenting ideas, but once a piece of code is written and debugged and is working, then it's much more common and useful to save it in a separate file and then use it as a method. So that's what we're doing here. Just to make sure that you all have this code, we are saving it from the Jupyter notebook. But now that it's saved, we can import all functions from this file by writing this command from the name of the module and then import. And let's run help. Remember, docstrings in user-defined functions are very useful because we can actually just read here what that function is supposed to do. We have here a module, ObjectExplore, and also a function called the same name. It didn't have to be like that, but I just named this one function in one module in the same way. So what is this ObjectExplore function? Well, it takes two arguments. Second one is option, but the first one is the variable that we want to explore. The optional argument can be a string with any combination of the following words. And what this function does is basically list attributes and methods of the class. We can look what different classes have as methods and attributes. Let's try to use this. You know, we go back to the data types in Python, and let's see. Let's make x a Boolean variable which holds false, and then just call an ObjectExplore in this variable. Ooh, we have a lot of output here. So what's going on? Well, first of all, this is false. This is what it's going to be about. This is an object report on that. The class of the object is Boolean. Well, we knew that. We called it a type of the variable, but it's actually a class which is called Boolean. The parent class here is the integer. Remember, there was something that we could use all the integer operations on Booleans, and this is exactly why. So there's this inheritance going on here. So Boolean is a special case of an integer, and so the methods of an integer apply to the Boolean. It occupies 24 bytes in the memory, and then it has public properties, public methods, and private methods. Private methods and properties are those which are not accessible from the outside, and this is what allows for the encapsulation concept to be used. Now, it's worth saying that in Python, there's actually this encapsulation is not strict. So in principle, I could do something with this methods or with this property, but by convention, everything that is enclosed into this double underscore, all methods and all properties in the Python classes are considered to be private. So to skip some of this input, let's just look at the public methods and properties. What do we have here? Well, in public properties, we have the real part and the imaginary part of the number, numerator and denominator, numerator and denominator. And so you can see that this has to do with the value. And then we have a few methods, such as converting to bytes and bit length and such. Interesting. Let's look at an integer. If I run this, we also see that this integer variable is an object. It's an object of the class int, It has its own parent, which is just the generic object class. It occupies a little bit more space in the memory. And it has public properties. I want to limit the output here as well. Public properties and public methods exactly as the Boolean variable before. We can do this to all data types. So here, for example, float. Let's look at private methods here. You can see there's a whole list of private methods. And these methods actually implement the normal operations on numbers that we would expect the floats be able to do. Such as, addition, that's basically a simple plus operation, taking the module, the absolute value. Here's the Boolean representation of this float, so that floats can be used in logical expressions. Equality checks, greater or equal, what else? Greater than, less or equal, less than. A lot of different things, and all of the standard sort of expected operations that we do with floats, they all have a corresponding method that implements these operations. Let's look at another one, string. String has also very long list of public methods. There's a lot of things we can do with strings, like, I don't know, swap case, or format in different ways, find inside of strings, count characters, I suppose. All of these properties are implemented. Now let's look at polymorphism for strings. So I've mentioned that polymorphism is basically a concept that allows the same operation, or at least seemingly the operation with the same name, to be implemented for objects of different type. So look at this. It turns out that the arithmetical operations are actually defined for strings. And this is an example of polymorphism where something that is not typical can actually be performed. So we can check for equality of strings. We can have addition for strings, and that basically works as concatenation. We can join strings together using the plus sign. Subtraction is not defined. Multiplication is defined, so multiplication with an int, with an integer, is basically a repetition of the same string. Division is not defined neither, but comparison is, and for comparison it's the ASCII codes of the characters which are used to compare in lexicographical order. So let's look at the example. Here we have two strings, S1 and S2, economics and econometrics with the spaces in the end. Well, S1 is plus S2 is just concatenated two strings, economics, econometrics. Let's try this one. Well, we get an error if we're trying to add an integer to a string. That's right. But if we convert the integer into string beforehand, then we get a concatenation again. What happens if we have this expression? We have S1 plus S2 brackets multiplied by 2. Well, as expected, it's going to be economics, econometrics, economics, econometrics. Well, and now let's test the distributive law for these operations. It doesn't hold, right? So you cannot open brackets in this way. Look here, we're doing almost arithmetics on the strings, and we also comparing them, so we're doing a logical operation. Pretty neat. Let's look at the variable which is list and explore the public properties and methods there. And you can see here is the list of methods that apply to the list. We can append, clear, copy, count, extend. Some of them pop, remove. Some of them we mentioned a video ago when we were talking about lists. There is something to explore further here. I should mention that the help functions apply here as well. So for example, we can write help x dot and then one of these methods. So for example, remove. remove and run this. And as you can see, we're getting the help on the method remove of this object. Now we could call this for a class itself as well. So the class is called list. List remove would give you the same thing. So that's how it's possible to learn about all these different methods here. For tuples, the number of possible things to do, methods, is of course shorter because tuples are immutable. So essentially we can count the number of members in a tuple and we can index into them. So the method index is used to get access to the elements of these collections. What about the dictionary? Well, dictionary has a long list of public methods and properties again. Remember, dictionary is a collection of pairs with key value. All right. Well, we've mentioned a couple of times inheritance in Booleans already, but here's how we can make sure that it's true again. A lambda function is another type of an object, and f here is defined as a lambda function, and we can look into this object f. So any function is an object, in fact, and you can see that there is a very large list of various methods. Well, these are the public. There are no public methods, but private methods which implement different standard operations with the function. So as a matter of the fact, everything is an object in Python. Variables of all types, functions, both custom and inbuilt, imported modules, files, pretty much everything is an object. So this object explorer function may be quite useful. In fact, a good integrated development environment would list the methods of objects that you're working with and properties of these objects for you automatically. So finally, how do we make objects? How do we write objects? Well, we've seen the example with Fibonacci series already, but let's also look at a couple of more examples of how to write an object and when to use them. So when should we use objects in economic modeling? Well, it turns out to be very helpful when we want to store parameters of the model. And the reason for that is that as we work with models, we may want to keep around a couple of versions of the models which differ in some parameters, but not in all of them. They are the same model, but we want to compare the results obtained from slightly different parameterizations. And then a model parameter can be stored, or a model itself can be stored as an object, and then we can call the methods of this object to simulate or to produce solutions. Now, sometimes you have, in one model, you have what I call complex and repeatedly used things, like some agents, for example, or some parts of the model that interact. And they're in principle the same, but they must differ in some attributes or some methods. So this not to be confused with a collection of functions, which is also a very useful concept, right? So as we said in the beginning, Python mixes all different styles of programming. And so you can have procedural programming, basically a collection of functions made into a module, and then some object-oriented programming where you store model parameters and objects as objects, or some more complicated, in some more complicated cases, you can store objects as objects. Now, what we need to learn is syntax of writing the objects. And you've noticed there is a lot of standard methods that must be implemented for different objects. And there is a nice list of all different standard double underscore type methods which apply in different situations. So this list is a nice source of the ways to implement standard operations for your own custom objects. So here's another example. The class is called firm, And docstrings are equally important in classes as they are in functions. And here we can see that this class is going to store the parameters of the production function of this functional form and implements this function. The class has the standard initialization method, the initializer, and that's defined in a very standard way with double underscore init. Now, classes always have to have self as the first argument in their methods. This first argument can be named anything, but it will refer to the instance of a class, to the object itself. And by convention, they're called self in Python. And it's usually a good idea to stick to the convention so that the code remains readable or becomes readable. As you can see, we can use Greek letters in Jupyter notebooks. I think they're done this way. Yep. It's a backslash and then the code number and then a tab. Okay, 0.5, ACE2, these are default parameters of the production function, and then they can be overwritten when we call the initializer, of course. This works in the exactly same way as with any other function. And now what happens in this line 6 and 7? Well, see, we are storing the past parameters in the attributes of the self, and that refers to the object. So we are storing the parameters alpha and capital A in the public attributes of the object. That's what happens here. Now imagine that this parameter was called A, the input parameter to the initializer. Then here it would be this alpha that needs to be changed to A. That's what the correspondence is. And then it's still saved into the alpha attributes of the class. And here's the production function. It just simply returns the formula as it is stated in the description. But to get access to the attributes of the class itself, of the self of that object that we will create from this class, we need to use self dot again to refer to the attributes of the class. And now value, that comes from the input argument of the method. The value at which we are computing the production function. Okay, I should run this code. So now that class is created and is loaded into the memory. And now I can use it. So how do I use it? Well, let's create firm1 using this just initializer of the class without any arguments. So this will have firm1 will have default production parameters. We can check what kind of object that is, firm1, and let's do that. You can see that the firm1 is the object of the type firm. It says over here. The parent class is general object. It takes so much time in memory. Public properties are alpha and A. Maybe I can look at the public properties and methods. And the public method is production. So here's our object. Let's create two more firms, firm2 and firm3, with slightly different parameters in their production function. And, using these three firms, we can calculate their production level for a particular input, particular level capital. And you can see that the firm 2 and 3, they are more productive than the default values, and that's reflected into. So this is a simple example of how to use objects in an economic model. We are using the firm object to represent different firms, but then we can have multiple firms in the model, which can differ by their attributes. Here's a more involved example. Here we are creating the class called Polynomial, and I guess I'll close my slides to be able to scroll this a little bit easier in Jupyter Notebook. So what's the idea under this class? You can see this implements the polynomial object and binary operations on polynomials. So the idea is that we can represent polynomials through their coefficients, and then I was thinking that it would be interesting to implement the addition and multiplication of polynomials using this class. And then, of course, we will have call so that we can evaluate, so we can call our polynomials on at a particular set of values. So let's first look how it performs. CP is going to be a polynomial created with these coefficients, and if I ask Object Explorer to tell me about this class, then this is the representation of the polynomial. You can see that coefficients are assigned in the ascending order of the powers. So 1 becomes the 1, and 2 becomes 2x, and 3 becomes 2x squared. This is the variable of the class polynomial inherited from object. It takes 64 bytes of the memory. There are public properties, coefficients, the degree of polynomial, and you can see degree here is degree 2 because the highest power in this polynomial is a square. Then it has something called rep, and that's a representation. That's a string that holds the sort of the human readable way of writing this polynomial. And there's a public method string, but of course there's also a call to this polynomial. So we can evaluate this polynomial, say at 10. We get an answer here, the output of 321. Does it look right? 321, yes it does. So let's see how the class is constructed. As with all classes, we have to start with the keyword class. Don't forget the docstring. And then, as with all classes, it's a good idea to have initializer. In principle, it doesn't have to exist, but the class will still work. But initializer is a good place to set the public properties, define them, and set them to their initial values. So you can see that the input arguments here is the list of coefficients called coeffs. Now, by default, it's a list with one element equal to 0, right? So by default, we get a 0 polynomial. But here we can calculate the degree of polynomial, and that's simply the length of the list minus 1. So a polynomial of degree 2 will have 3 coefficients. This second line calculates or computes the representation of the polynomial. Let's get back to that. And the coefficients are simply stored as the public attributes. Now, this standard function double underscore wrapper, that's what's called when you say print a particular variable of this class or a particular object of this class. It returns the representation, self-wrapper. Okay, let's look at what this wrapper actually is. See here in line 13, it returns the string representation, which is already saved as the property of the class, but it is created over here at the initialization by the method called string. Let's first look at this code here. So what happens here is that first we use list comprehension. Remember that from video number 4 or 5. Where we are building the list for k in range between 0 and the number of degrees plus 1. So we are ranging through all the coefficients, and if the coefficient is not 0, then the list element becomes equal to the string representation of the coefficients, and then followed by x to the power of the string representation of k. So that basically builds a list of the access to the right power with the right coefficient. Now, if the length of this list is 0, so that means that all of the coefficients were 0, then the polynomial is 0, and the string representation of that is just a string with 0 character in it. But otherwise, we want to eventually join the terms of this, these terms, join the elements of this list which are all strings, right? This is a string representation, and the pluses over here mean that we join the string together. So we want to join the elements of the list using the space plus space character. And that will give us this nice representation over here, where 1 is joined with space plus space, with 2x, space plus space, 3x squared. Now, you notice that 1 doesn't have x to the power of 0, and this is basically done with these two strings over, two lines over here. The 0th term is going to be just equal to the string representation of the coefficient if the coefficient is not equal to 0. If the coefficient at the place 0 was equal to 0, then maybe the term, the 0th term does not correspond to the 0th power, and therefore we don't change it, else we just keep it as it is. And the same thing, we replace the term 1 with the string representation of the coefficient of the first power followed by x, simply by x without any power 1. And that's, of course, if the coefficient is not 0 in a particular power, but we also have to check if it exists. And now if it doesn't exist, so the length is less than 1, then the first condition is not checked because of this AND logical operator. And of course, if you have false, then it doesn't matter what the second one is, and it's not checked. Now, if this condition does not hold, this one, then we just keep this term 1 unchanged. And so this function basically builds a human-readable string representation of the polynomial. Very nice. Okay, let's go to the interesting parts. Addition of polynomials. So when we say plus and minus, this is what this is the function that is being run. And we can see over here in this cell that if we define polynomial p1 and polynomial p2, then p3 can be added. Can be a sum of the polynomials p1 and p2. So in this example, p1 is 1 plus 2x plus 5x squared plus 4x to the 5th. And p2 is 10 plus 3x squared plus 7x cubed. And the sum of them is just simply sort of a sum over the of these two polynomials. And you can see how it's done, right? It can be done sort of by summing up the same powers of the two polynomials. And this is what this function implements. Well, it overloads the plus operator. That I should say defines the plus operator, the summation operator. You can see over here in the example, we're just saying p3 equals p1 plus p2 very neatly, and this the sum is basically calculated by the polynomial object itself. How is this done? Well, we first calculate the maximum length of the polynomials. Oh, by the way, so this add is has two arguments. Self argument, which is the standard and always there. That's the polynomial to which we are adding. And then this other, which is the other polynomial that we want to add to it. We could, in principle, check here that this other is a polynomial and not, say, an integer or a list. The other can be, in principle, any variable, but we are thinking that this is going to be applied only to polynomials. So then we start building this self-temp, the temporary storage for the coefficients of the result. And, oh no, I'm sorry. Here we're making a copy of the self coefficients, and the idea is that we are adding the number of zeros, which is the difference between the maximum degree and the number of coefficients that this polynomial has. And we do the same with the other polynomial. And this is just to ensure that self-temp and other temp has the same number of elements in these two lists. And then, once that is done, we can invoke the list comprehension again. And here we are following I from all the way up to d minus 1, right? And we're just basically building the list by summing up the coefficients of these two polynomials. Now, an important this lands into the new temp variable. The important thing is that we return something that should look familiar, and this is essentially initialization of a new polynomial object. So there is a bit of recursion here. So in order to add two polynomials, we are creating the third polynomial from the list of coefficients formed, given the summation operation. Now, multiplication operation does the same thing for multiplication, and it's a little bit more involved here. You have to wrap your hand around this double loop. What happens is that we are creating the coefficients of the product, and this is a cross product of the two lists of coefficients, and so it will have the degree which equals to the sum of the degrees of the arguments, and this is the list that we are preparing for the coefficients of the new polynomial. And then the double loop here, we initialized all of these coefficients with zeros, and then we are adding the products of the ith coefficient of the first polynomial and the jth coefficient of the second polynomial, and we look at all possible combinations of i's and j's over here in this in the nested loop, in the nested for loop. Now, the product is added to the coefficient with the index I plus j, and this is how we sort of multiply and sum the identical terms in the same double loop. And again, the result is a polynomial created from the new list of coefficients. Now, finally, let's look at this call function. And this simply evaluates the polynomial at a given value, value given by val. Here, a result is going to be accumulated using a loop as well. So we initialize the result by looking at the coefficient that doesn't have any x, the constant. And then x is initialized to the val, the value where the polynomial has to be evaluated. And then look here, we just go through all coefficients of the polynomial using I plus 1 to index. So this is starting from the second coefficient. And we add to the result the x multiplied with the corresponding coefficient. Now, how do we get the higher powers of x? Here, it seems that we are using only x multiplied with the coefficient. There is no power operation. Well, in the same loop, we're actually multiplying the variable x with the value every time we go to the next iteration of the loop. So instead of calculating the powers, we are incrementally multiplying x with the value again and again, and that saves some time actually. So we'll probably come back to this example when we talk about algorithms next week. Okay, so going back to the example here, and I can go back to the slide mode, I suppose. You can see that we're creating polynomial p1. And we're printing that, and we are evaluating p1 at 0.5, and this is what we have here. And then we have p2, and we print that and evaluate p2 at the 0.2. And this is how they are evaluated. We're just using the object created from the polynomial class directly as a function. This is then invokes the call method and returns the value. And as I already said, we can sum them up. And here's the result of the product of the two polynomials. The highest power is 7, and this is basically 5 plus 3 here, right? So the sum of the powers of the underlying polynomials. You're welcome to check this correctness of this product using pen and paper, essentially. So this concludes the video about the object-oriented programming. A couple of further learning resources. Here's a very simple explanation, a video with very simple explanation of the concepts of OOP. you can resort to that if you still find it a bit confusing. And just to put here in the list of learning resources the standard method of Python, which is a list that is good to know when you want to implement standard operations on the objects that you write yourself. Well, see you next time.